Video 2 of Chapter 9, we are actually going to carry out a full-on hypothesis or significance test of a proportion. Now we're going to go back to our Mr. G Rubik's Cube example, where he claims 75% of the time he can solve a Rubik's Cube in under 75 seconds. And so we tested this claim, and a random student was selected every day for 50 days to scramble a Rubik's Cube and let Mr. G solve it. They timed him. They found out that in actually 30 of the 50 days, which was a 60% success rate, he could actually solve the Rubik's Cube in under 75 seconds. Now, in video 1, we used a simulation to estimate the p-value to make a conclusion about the 75% claim. Now, that simulated p-value is not perfect by any means. We found, based on a simulation of 50 simulated situations, that we got a p-value, a simulated p-value of 4%. What we're actually going to do in this video is figure out what is the legitimate p-value so that we can actually make a better informed decision about whether we should reject or fail to reject the null hypothesis. Now, for hypothesis testing, this is going to look pretty similar to our last chapter with confidence intervals. We're still going to talk about the 3 C's, conditions, calculations, and conclusions, but we also need to add in our hypotheses, our null and alternate hypothesis. So for our hypotheses, to begin that, you need to state what is the null and the alternate hypothesis. Now, for the null hypothesis, we said we're always going to use an equal sign here, and then whatever the claim is being made, we're going to assume that that claim is true. And then for our alternate hypothesis, we said there's one of 3 symbols that are going to be used. And typically in a problem, it will be clear what symbol you should be using for the alternate hypothesis. You don't get to decide after the sample has been taken, though, which inequality symbol you're going to use for the alternate. So you may read a problem and they may say, here's the claim, but we're looking for a change, a positive change, or we're looking for an increase. So then you might go, oh, well, I want to say it's greater than if they're looking for an increase. Or a problem might say they're looking to reduce a particular value. So you would put a less than there. Now, there's going to be times where a problem might state they're just looking for a difference in general. They don't know which way from the initial claim in the null hypothesis that the alternate is going to go. So if they just are looking for a difference, then we would use not equal to. We don't know if it's going to be greater than or less than, or maybe we don't care if it's greater than or less than. What we care about is that it's not that specific number. Now, you also need, and this is the one thing that I typically have to harp on students to do, is you need to define what your parameter is in the problem. So if we use lowercase p to define the population proportion, you really need to define, well, what is the population proportion of interest? What is it in the context of this problem? So again, not only writing your null and alternate hypothesis, but tell me, what does that parameter value really mean? So for our Mr. G problem, and again, we talked about these hypotheses in the last video, but the null hypothesis is we're going to go with Mr. G's initial claim that it really is 75%. But we said we feel like that's probably not true. We probably feel like it's less than 75% of the time. So we're going to go with less than here. I did mention in the previous video that maybe we don't know if it's 75%, and we don't know if it's smaller or bigger than 75%. Like maybe Mr. G's just, he doesn't want to brag. He's like, 75% of the time. Maybe in fact it's like 90%. So we could have said not equal to 75% if we didn't really think it was 75%, but we didn't really know if it was smaller or bigger than 75%. So I said that is a possibility, but we're going to go with the less than scenario. And then I need to define what P represents here. So P equals the proportion of the times that Mr. G can solve the Rubik's Cube in under 75 seconds. So again, this is kind of step 1. Once you write the hypotheses and you define what your parameter value is, then essentially we get to go do the 3 C's like we did with confidence intervals last chapter. There will be some small differences here and there, but the conditions for the most part are going to look very, very familiar. So they're the same 3 conditions. We have the random condition, the independent condition, and the normal condition. Now, the random condition is to basically establish an unbiased center. And again, you have to be explicitly told that your sample was a random sample or it was an SRS. For the independent condition, this is for us to be able to have a usable standard error formula for the standard deviation. And so we just had to check, is the population at least 10 times our sample size? And if it is, great. And if it's not, technically there's a way around it. There's a bigger, longer formula for the standard error. But really, for the most part, unless the problem states, why can't you do this problem? This is going to be one of those assumed true situations. And then the normal condition. Really, that's to establish the shape. We need our sampling distribution to be approximately normal so that we can actually calculate a probability. We're going to be using normal CDF again this chapter. Now, here's what gets a little tricky. Is back in chapter 7, when we first did sampling distributions, we did n times p and n times 1 minus p. And the thing was, back in chapter 7, they gave us the population proportion value. And then last chapter, in chapter 8, when we did confidence intervals, we were trying to capture the true population proportion value, and we didn't know what it was. So for the normal condition last chapter, we said, well, we don't know what P is. We don't know the population proportion. So what can we do if we don't know P? We said we're going to substitute it out with its next best replacement, and that was P hat. Now, we're coming to hypothesis testing. And you might think, well, we don't know what the actual population proportion is. But if you consider, that's our null hypothesis. So the rule of thumb is if you have a population proportion, if you have P, you should use that value. If you don't have the population proportion, but if you have a claimed population proportion, like we are going to have in this chapter, you should be using the null hypothesis value for the normal condition here. Now, in the worst case scenario, if we don't have the actual population proportion, if we don't have a claimed population proportion, then we have to use the sample proportion. We would have to use P hat. So we're switching back. We're going to use P, which is going to come from our null hypothesis. So let's check the conditions for our Mr. G problem. Now, the random condition did state, it says that a random student was chosen each day for 50 days. And not only that, really the Rubik's Cube was scrambled by this random student. So to me, there's kind of like these two aspects of randomization, like the student was randomly selected and the whole act of mixing up the Rubik's Cube needs to be random so that Mr. G doesn't have like advanced knowledge of how to solve the Rubik's Cube. For the independent condition, is the population at least 10 times our sample size? Well, what was our sample size? Well, our sample size was 50 days. So 10 times 50 would be 500 days. And so the population would be all days. And can we assume that Mr. G could solve this Rubik's Cube in more than 500 days worth of days? And absolutely, that would be okay. So we'll just say assume true. And then for the normal condition, is n times p greater than or equal to 10? And is n times 1 minus p greater than or equal to 10? Well, remember n was 50, and p, which was our claimed population proportion, was 75%. So really what we're stating is, out of 50 days, if 75% is really the truth here, out of those 50 days, how many successes would we expect to see? And how many failures would we expect to see out of those 50 days? So 50 times 75%, it doesn't come out to be an awesome whole number, but we get 37.5 is greater than or equal to 10. And then how many failures would be the leftover of the 50 days, which in this case is 12.5. So again, both of those are greater than or equal to 10. So the sampling distribution. And we can abbreviate distribution, but not sampling. You may never abbreviate sampling. Just write out the full word. The sampling distribution is approximately normal. And again, this is going to allow us to use normal CDF later in the calculations. So now let's talk about the calculations. On the AP Stats formula sheet, you are given this really not too terribly helpful formula for how you're going to calculate the standardized test statistic. And really, the standardized test statistic in this formula really is the same thing as our z-score formula that we once upon a time used back in Chapter 2. Now, the only thing that looks really exactly familiar here would be the z equals and z equals. The x represented the value that we were kind of given. Mu was the mean and sigma was the standard deviation. Now, if you consider here, we really can tie in what we have previously talked about, how the mean really is p, right? Because once upon a time we said mu sub p hat is equal to p. So the mean really is the population proportion value. And then we also used the formula back in Chapter 7 that sigma sub p hat was equal to the square root of p times 1 minus p over n. And notice, that really is the same standard deviation that we're going to use here. Now, in terms of actually doing the calculations, I'm going to show you two different ways, just like I did with confidence intervals before. I'm going to show you how to do it really by hand, if you prefer to do it the long way. Or I'll show you the fancy calculator command, where you can just punch in the values that was given to you in the problem, and you can get the p-value in the end. But if you want to do it by hand, you can plug in all the values for p hat, for p, for p, for p, for the sample size, and we can get what that test statistic is. Now, here's the thing. That test statistic is either going to be positive or it's going to be negative. And so whatever value it is, whether it's positive or negative, if it is negative, if it is a negative something, then our probability that we're going to calculate, our p-value, we're going to say, what's the probability that we would find other test statistics that are further away from our claimed value? And further away, if it's negative, that means it's already on the left side of the distribution. So we're always going to say less than if we have a negative test statistic. Now, there are going to be times where maybe we have a positive test statistic. And so if we have a positive something, 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 then we're going to be on the right side of the distribution. And so we're going to say, what is the probability that we would find other test statistics that are greater than this particular value that we got? And so we get to use normal CDF, and we need to input in a lower bound and an upper bound, and there's going to be a positive infinity or negative infinity depending on that sign, if it's going to be greater than or less than. And since our test statistic is using the standard normal distribution, because it's a z-score technically, then the mean and the standard deviation will be the default 0 and 1. And whatever value we get out of that normal CDF command represents our p-value. Now, what is really important here is on the AP exam, obviously the p-value is the thing that we're after. But on the AP exam, not only do you have to come up with the p-value, but you also need to state what that test statistic was, what that z test statistic value was. So I need to know what is the test statistic and what is the p-value in that problem to get full credit. Now let's talk about for the calculations with using our calculator. Now, if we want to use that special calculator command, we have to name the procedure first. We have to name this a one sample z-test for a proportion, or for p. And on our calculator, we need to go find the command a one prop z-test. Now, if we hit the stat button, we go over to tests. I believe this is number 5 on our list, a one prop z-test. And so when you open that up, you're going to see this lovely list here. Now, p sub 0, this is really p naught, and this is our hypothesized value that we need to input as a decimal. Even though our proportion may be a percentage, we have to be able to put this number in as a decimal. X and n are going to represent our sample proportion. The x is the numerator of our sample proportion, and n is our denominator for our sample proportion. And then for prop, this is where the alternate hypothesis comes into play. Is the alternate hypothesis not equal to the claimed value? Is it less than the claimed value? Or is it greater than the claimed value? Whichever one of these it is, you put your cursor over it, press enter to select it, and then come down and hit calculate. Now, once you hit calculate, you will see the z-test statistic, which you must write down and identify as the test statistic value. Say z equals and give me the number. And you also have to provide the p-value. And the p-value will just say p equals. And you must write down that number as well. So let's see what that looks like by hand now. So our sample proportion was what? 60%. Our claim was 75%. Now, automatically right now, if you look at this numerator and we're taking 60% minus 75%, we're going to get a negative test statistic. And again, what does a negative test statistic mean? It means we're on the left side of the distribution, which is perfectly fine. So don't freak out when you get a negative value here. Now, we also have the standard error, 0.75 times 1 minus 0.75 divided by our sample size of 50 days. And so when I type that in my calculator, you do want to make sure that you put that numerator in parentheses. Otherwise, only the 0.75 up here will get divided by the standard error. And we want really this whole thing to be divided. So when I put that into my calculator, I get approximately negative 2.449. Now, what that means is that 60% is almost 2.5 standard deviations below the mean of 75%, where I would expect to be. So that z-score, that test statistic, really represents the same thing that we had talked about previously in Chapter 2. But now we're going to take that test statistic, that z-score, and convert it into a p-value, a probability value. So now we want to find what is the probability that we would find other test statistics, other z-scores that are more extreme or as extreme. So we're going to say less than or equal to. Remember, including this negative 2.449 really adds no extra probability, but we go ahead and include it. Now, remember, we're going less than because our test statistic is negative. And so we get to use normal CDF because we verified the normal condition. And so in this scenario, we want all other test statistics that are as small or smaller than negative 2.449. So that means we're starting at negative infinity, going up to negative 2.449. There we go. And then again, the mean and the standard deviation, because it's a standard normal distribution, since we're using z-scores, will be 0 and 1. So I'm going to label lower bound, upper bound, mu, sigma, and that comes out to be approximately 0.007153. And that, ladies and gentlemen, is our p-value. Now remember, don't just circle the p-value, we also need that test statistic. That z was approximately negative 2.449. That led us to the p-value of 0.007153. So what does the calculator command look like for our Rubik's Cube problem? So I named the procedure. It's a one sample z-test for a proportion or for p. I used my one prop z-test. So the claim is that Mr. G can solve the Rubik's Cube 75% of the time in under 75 seconds. So that 75%, 0.75, is our claimed value. But what I saw from my sample was that 30 out of 50 times, there's our sample proportion, he was able to do it in under 75 seconds. For the alternate hypothesis, we believe that it was actually less than 75%, so I selected the middle alternate hypothesis here, and when I hit calculate, then I got my results. Initially it says prop less than 0.75, there is our alternate hypothesis, and then the test statistic, the z. Again, you can round this to 2 or 3 decimal places, is perfectly fine, and the p-value is the one right below it, so 0.007153. Now, p hat, that's just our 30 out of 50 sample proportion. It's just written as a decimal now, which is fine, but you don't need to write that number down. And it gives us our sample size of 50. And so now our new conclusion statement is going to be different than what it was for our confidence interval chapter. And initially, before we write our conclusion statement, we need to think about, well, what decision are we going to make? Are we rejecting or failing to reject the null hypothesis? So depending on what your p-value is compared to your alpha or significance level, you'll first need to decide, am I going to reject or am I going to fail to reject? And then we get to write our actual conclusion statement. So we are going to state that we do have enough evidence at the alpha equals 0.05 level to conclude the alternate hypothesis in context, but we say that we do have enough evidence if we reject the null hypothesis. But if we fail to reject the null hypothesis, then we say that we do not have. So remember, if we fail to reject the null hypothesis, then we state we do not have enough evidence. And then again, you tell me what that alpha level is. Don't just leave it blank here. Tell me it's 0.05, it's 0.01, it's 0.10. You can list it as a decimal or as a percentage. It doesn't matter. And then again, you have to tell me what is the alternate hypothesis in context. Now, it is important that not only do you write the concluding statement, but you also need to include how the p-value compared to your alpha or significance level. So again, it is important that you do this whole statement and you also tell me how the p-value compares to the alpha level. On the AP exam, they're going to be looking for that piece of information right there with your conclusion statement. So what does that look like for our Mr. G problem? Well, remember the p-value, let's write it out here, it was 0.007153, and that value is clearly less than an alpha level of 5%. So our initial decision is that we are absolutely going to reject the null hypothesis. So again, I need this. And on the AP exam, you need that. That's called the linkage. It's linking together what actually happened with our significance level. So now we're going to state that we do or do not have. Which way did it go? Well, since we reject, we do have enough evidence. We do have enough evidence at the alpha equals 0.05 level to conclude, and remember, we're trying to conclude the alternate hypothesis. What was the alternate hypothesis? To conclude that the proportion of times Mr. G can solve a Rubik's Cube in under 75 seconds is less than 75%. So remember, that's the alternate. We thought it was less than 75%. So we do have enough evidence. Mr. G does appear to be a statistical liar here. Now, again, I mentioned previously that maybe there's a chance that Mr. G really is telling the truth, and we just made a bad choice here based on our one sample. That is entirely possible. So again, into the chapter, we'll talk about errors that could happen based on our decisions. So I have a you-do problem here. The test statistic Z for a hypothesis test is determined to be 2.163. So imagine I already did all the dirty work for you, and I said, here's the test statistic. What I want you all to do is to calculate the p-value and make the initial decision. Just tell me, are you going to reject or fail to reject the null hypothesis with an alpha or significance level of 1%?